about 10 minutes after we finish the problems, just for questions about the class or SI or VSI or whatever I can help you with. But just as far as how Zoom is going to work, so I mean, clearly you guys are on it, so you understand how to get here. But I know it's a little different because you guys are not actually in the session with us, but we still expect some form of participation, right? So we have the chat feature. So if I'm going to ask you a question, I would really appreciate it, and I sort of expect you guys to reply in the chat, sort of like if you guys have been to the real SI session, sort of, so just everyone adds to the topic and everybody adds to the discussion, just to make sure we're getting everyone involved and everyone understands what we're trying to get done here. So that's going to be a big thing. All your mics and videos are muted, but we're going to be doing pretty much all of our contact with each other through the chat. So if I ask you a question, that's where your answers are going to go. Yeah, so I'll be the only one with the mic and the video on. And so how it's going to work is I'm going to give you guys these questions. You should also be able to see them on the PowerPoint that I sent out, which I have open here. But if you can't, you can just always look at my screen. I'm going to have it open the whole time until we start actually working on the problems. So yeah, so just to show you real quick before we get started, like on this first question, I have these questions on the right. So I'm going to expect you guys, before we even work on it, we're going to discuss the problems a little bit. And I'm going to ask you guys questions, and I sort of expect a response from everybody just to make sure we're on the same page. And I probably won't move on until at least get most of the session to respond. So I would really, really appreciate it if you guys could just use the chat and give whatever answers you have. So why don't we get started with the first problem? So we have one question. So we have one car on the left that is moving at 65 miles per hour with a radius of 10 meters. We have a car on the right that's moving also at 65 miles per hour, but on its track, it has a radius of 7 meters from the center. So before we get started with the question, I want you guys to sort of just think about and then answer, what car do you think will have the higher centripetal acceleration, just based off of the information I've given you right now. Just based on the radius that you've been given and the miles per hour of each car, which car do you think will have the higher centripetal acceleration? Before we get started with actual like math and calculations. All right. Okay. So everyone seems to be in agreement, right? That the one with the smaller radius, or in our example, the car that's only 7 meters away from the center, is going to be the one with the higher centripetal acceleration. And you guys seem to understand, because the formula, we know that the centripetal acceleration is equal to v squared over the radius. So since the radius is on the bottom of the fraction, we can tell that for any problem really, when the cars have the same magnitude of their velocity, we know that the car with the smaller radius is going to have the higher centripetal acceleration, just because when you're dividing by a smaller number, you end up with a bigger number. So we all seem to be pretty clear on that. So for about the next few minutes, actually working on the problem, I'm going to have you work on the actual question. So what is the centripetal acceleration of each car? And I want you guys to make note that you're given the velocity in miles per hour and you're given a radius of in meters, but your answer is going to be in miles per hour squared. So you're going to have to figure out what the conversion factors are for each unit to try to end up getting miles per hour squared. And so I'm going to give you guys about 10 minutes to work on that. And then you guys can use it. Hopefully you will discuss in the chat any issues you have, any questions you have for me, any questions you have for each other. But for the next couple minutes or so, we're just going to work on that problem, and then we'll get back as a group and we'll work on it together. Okay, so hopefully you guys can figure this one out. Hopefully, if you have any questions, do not be afraid to use the chat. Do not be afraid to ask each other or ask me. I'll keep my eye on it. Hopefully you guys keep your eye on it too. But yeah, for now, just what is the centripetal acceleration of each car? So good luck with that, and then we'll get back. We'll regroup in a few minutes. The conversion factors that you guys are going to need to the PowerPoint. So in case you guys can find them, or just to make sure we're all using the same exact numbers, I added them. And so, yeah, I'll give you guys a couple more minutes on this one till about maybe around 10:20ish. But please, as soon as you have an answer, please put it in the chat. And then if you find that somebody has a different answer than you, maybe you can sort of discuss it. But yeah, please, as soon as you have an answer, please send it in the chat just to make sure everyone's working on it and everyone is doing the problem. Okay, I'll give you guys a couple more minutes on this one and then we'll group back together. Thank you. All right, so I noticed a few more people have joined the session. So what we're doing right now is, if you can see my screen or you have the PowerPoint open in front of you, we'll work on this problem here where the question is, what is the centripetal acceleration of each car? So you have one car that's going 65 miles per hour on a 10-meter radius circle, and then the other one's going 65 miles per hour as well, but it's on a 7-meter radius track. So we're currently working on the problem. We'll probably keep working on it for another few minutes or so. Highly encourage everybody that just joined to be as active in the chat as they need to make sure everybody understands the question and asks questions, and then ask each other, help each other out, but also ask me if you need. And then so make sure you guys put in your answers though, because we won't be moving on to the next question until this question gets answered. So please, everybody, as soon as you have an answer for this one, enter it on the chat. And so I'll give you guys maybe about 3-4 more minutes to work on this one, and then we'll come back together and discuss it. Thank you. Okay, so I'm starting to notice some people are putting their answers in the chat. Please keep it up. Everybody else who has an answer also put their answers in the chat also as well. And then if you find you got something different from someone else, you can discuss it, but you still have a couple more minutes on this problem before we get to solving it. So yeah, as you guys start to get the answers, please share them, please discuss them. If you get something different, I would really appreciate that. Probably come back together at about 10:25, so about 4 more minutes, and then we'll solve the problem together. So I'll be showing you how I did the problem on the screen. But yeah, about 2-3 more minutes, and then we'll all come back together. Thank you. Okay, so before we move on, not everybody has actually put in an answer. So if you're actually able to put one or you solved it, I'd really appreciate it if you could send it now. I sort of don't want to move on until everybody has gotten a chance to answer. So for the next minute or so, if you do have an answer, could you please put it on, into the chat before we move on, just to make sure we're all on the same page, or it's so we can clear up any mistakes or whatever it is. So if you do have an answer, I'd really appreciate it if you could send it. And before we move on, just send in whatever answer you have. All right, so now that we have that, we're gonna move on to actually solving the problem. So we already discussed how we know that the car on the right is gonna have the faster centripetal acceleration. We determined that because we know the formula is v squared over r. So it makes sense that the one with the smaller radius would have the faster centripetal acceleration. So when it comes to exams that you have like next Tuesday, or I should say midterms, that's something you should really keep in mind, just being able to sort of think about the problem before you get into it. So when you actually get to the test, you know, you're not going to know, you're of course never going to know if you have the answer exactly right, but you have at least something to guide you and just sort of help you make sure that you're on the right path at least. All right, so we're going to answer this question. So we are going to use this is called the whiteboard. So we'll be able to solve the problems. All right, so we have one car that's going, so we'll say car one. We know that one's at 65 miles per hour. And we know the radius is 10 meters. We also have car two. And that is also at 65 miles per hour. And the radius is at 7 meters. So starting off with the first one, so we know that the centripetal acceleration is equal to v squared over r, like we discussed earlier. That's part of the reason that we know that car two should have the larger number. So if we want to plug in our values that we're given, so we are given 65 miles per hour, 65 miles per hour, and then that is squared. And then that is over our 10 meters. So my answer is going to be in miles per hour squared. So that might be a little bit different than what you have, but it's okay. As long as the answers end up being same with respect to their own units, it's not so much of an issue because we're not too worried about the units for now. As long as you know how to do the conversions, what units you end up with in this particular problem won't matter so much. Of course, probably on the midterm, it's going to be specified. But as long as you got the right answer using your units and you've shown that you can solve using whatever units, and that you can use dimensional analysis to get the right answer, it's fine. So while I might get a different answer, as long as it makes sense and it agrees with yours, they don't have to necessarily be in the same units and they're going to be this different number. So don't worry too much about that. And like I said in the PowerPoint, we know that there is 0.3048 meters per foot. And we're going to use feet, so we can convert that back into miles. So 5,280 feet per mile. So what ends up happening here is we have 65 squared, which is 4,225. So that's miles squared. And since we're dividing by hours, we can put that on the bottom. So we're going to have times 10 meters times hours squared. So then when we multiply that by 0.348 meters over 1 foot, we can cancel out these meters. And then when we multiply by 5,280 feet over a mile, per 1 mile, we can now cancel out this top. We can cancel out that squared because we don't want that in our final answer. We're looking for an acceleration. Acceleration is some units of distance over time squared. So, and that's what we end up with. That's what we end up with here. So these feet cancel out. Oops, that should not be. That is in miles. All right, so those miles cancel out, these feet cancel out. So what are we left with? We're left with these hours squared, and then we're left with the original miles. So if we plug that into our calculator, so we have 4,225. And then using significant figures, if we go back to our original problem, we can see that our limiting significant figures is the 65 that we used earlier. So we know our answer is going to have 2 sig figs. Actually, I'm sorry. We're going to know it's going to have 1 sig fig because we are limited by the 10 meters that we were given earlier. So 4,225 divided by 10 times 0.3048 times 5,280. So we are left with 679,948. 948. Oh gosh, Zoom's being a little tricky. So 679,948 miles per hour squared. But like we just discussed, we know our answer is going to end up having 1 sig fig. So that's going to round up to 700,000 miles per hour squared. So that is a huge number, right? So it does seem a little bit, it seems a little weird why the acceleration so fast when it's only going 65 miles per hour. But if you can, so going back to being able to visualize for the midterm, when something's going that fast around a small track, that seems almost impossible, right? So it's going 65 miles per hour against a track that's only 10 meters in radius. That's really, really fast for something that's so with such a low radius. So so it really does make sense that we end up having such a weird answer. So we know that car one has an acceleration of 700,000 miles per hour squared. So now we're going to move on to car two. So we can remove all this now that we kept track of that. We can keep all the other information because it is the same conversion. The only thing we're going to end up changing is the radius. So that radius is going to go away, and we're going to be left with 7 meters now. And like we discussed, this number should be bigger. So that's going to be a huge indicator on whether or not our answer is correct. So we're going to end up doing the same thing. We know that 65 squared is 4,225. That's going to be miles squared over 7 meters times hours squared. Because it's dividing, so we can just put that on the bottom side of the fraction. We're going to multiply that by the the 0.3048 that we had from earlier. Divide that by the 1 foot times the 5,280 feet that we have over 1 mile. Units cancel out, miles, feet, meters. So what are we left with? We're left with miles per hour squared. Just like we did earlier, plug that back into our calculator. Only difference is we are dividing by 7 now, not by 10. So when we plug this in, we get 971,354 miles per hour squared. But because of our limiting factor with our significant digits, we know that's only going to have 1 sig fig. So our real answer is going to be car 2. Our A is going to be, we're just going to end up rounding that up to 1 million. So it's going to be 1 million miles per hour squared. So now that we finished solving the problem, let's think about it. When you finish your midterm problem, it's going to really help if you just sit there and you look at what your answer is and compare it to your pre-question thoughts. So when we first looked at the question, we determined a few things. We determined that car 2 should have the higher acceleration, right? So does car 2 have the higher acceleration? Yeah. And then after we solved for car 1, we talked about how when something's going really fast all along a track with a small radius, it makes sense that the acceleration is huge. They both have huge accelerations, and car 2 has a higher acceleration. So we might not know 100% that these answers are correct, but using our analysis from before the question, we can realize that we might not be completely correct, but it does seem like we are. So we can be confident in our answers. So that is all we're going to have for question 1 when it comes to centripetal motion. These are just the foundations of centripetal motion. So if you ever have to move on to a tougher problem, it really boils down to these type of fundamentals. So that should really help for the midterm next week. All right, so moving on from this, we are going to move on to our second question. Please put any questions in the chat if you have any regarding this question. Please, if you guys are not clear on anything, if you had a different answer than me, please let me know and we'll cover it. So I don't want anybody to leave this like they didn't know what happened or they got lost somewhere. But so yeah, please let me know in the chat if you got lost anywhere, and then I will be sure to answer your question. But for now, we are going to move on to the next one. All right. So, we are going to go back to our PowerPoint. So the next question is a projectile motion question. So we are given some projectile that's moving at an initial velocity of 32 meters per second. It's at some angle 50 degrees. So some angle theta is 50 degrees. So those are our only two givens for this equation, for this problem. We are given the initial velocity and we are given theta. And the question is asking us, so what is the height of the projectile at 2 seconds? Excuse me. At what time t is the projectile at its highest point, and what is the value of that highest point? So in meters, what is the highest y value that the projectile reaches? And at what time t does the projectile hit the ground? And how far in the x direction does that projectile travel once it hits the ground? Okay, so similar to what we did in the previous problem, we are going to sort of discuss what can we determine before we start working on the math side of the problem. All right, so what do we know that we can use to find t and y at the projectile's highest point? So I'd really appreciate it if you guys answered that in the chat. What do we know when a projectile is at its highest point that we can use to solve for this stuff, given the information, using the givens that we have from the question? So you guys can just put that in the chat before we move on. I'd really appreciate it. I'll give you guys about a minute or two just to think about that. And then if you don't know, you can just say, I don't know, and then we'll talk about it. But I would appreciate it if everybody could give a response before we move on with this problem. So yeah, so I'm just gonna highly encourage you guys to think about this, give an answer. It's really important that you guys do this before any problem, just to make sure you can. Okay, so I see a couple answers. Appreciate it if everybody else also put an answer before we move on. Give you guys about another minute or so to think about it, and then we'll come back and discuss. All right, so I see an answer. So yeah, so that's true. Thank you, Javier. So we know that the velocity will be 0 in the y direction once it reaches that highest point. That's what we're going to use to determine when the projectile is at the highest point. And so moving on to the next one. So how can we find x after the ball has hit the ground without being given t, right? So if we go back to our problem, there's not much we know about it when it's going in the x direction. So what? So how would we find what that, like? What two things would we have to connect in order to find out when it hits the ground in the x direction, using the limited knowledge that we have about the ball moving in the x direction? Because if we plug that into using our variables, we probably would not get anything right now. So we probably have to use some other method of finding it. So I'll give you guys another minute or so to think about that, and then we'll come back together and discuss it. All right. So coming back together for this problem, that might be a little bit tough. Okay. Yeah, it's true. So thank you again. So we need the initial velocity in the y direction. Yeah, we can figure that out. So the key part to thinking about when it's going to hit the ground and finding the distance in the x direction is it's when a ball hits the ground in the y direction is the same time it hits the ground in the x direction, right? Because it's hitting the ground. It's no longer moving. So it's going to be the same time. So if we can figure out the time then, we can figure out the time now for the x direction. So if we can figure out when it hits the time in the y direction using what we're given, we could also find out in the x direction. So going back to these problems, we're going to take about the next 10 minutes to try our best to finish all these problems. And then in about 10 minutes or so, we're going to come back together and we're going to solve them together. All right, so hopefully you guys ask any questions you have in the chat. Please work together, ask questions with each other, ask me. But for now, work on the problem, and then hopefully we'll come back together and we'll get it done. All right, cool. Thank you. I will see you guys in a few minutes. All right, so we are going to get started on working on the problem. Hopefully you guys can follow along with what I am doing, and it'll be very similar to what you had. So going back to our whiteboard. So we know with a projectile, so what do we know? We know that V naught in no particular direction is 32 meters per second. 32.0 meters per second. That's equal to V naught. Stuff seems to be disappearing. So V naught is equal to 32.0 meters per second. Need Zoom to work with me here. Okay. Just give me 1 second. Just having some technical difficulties here. Let's get back to the whiteboard. All right. Back to this. So V naught is equal to 32.0 meters per second. Some angle theta is equal to 50 degrees. So what's the first question asking? Our first question is asking, what is the height of the projectile at time t is equal to 2.0 seconds? So using our kinematic equations, we know that y is equal to y naught plus v naught y times time plus 1/2 acceleration times time squared. So if we want to plug that in so we want to plug in our values. So we know y is equal, so our y naught is 0 since the object started from the ground. We know our v naught from earlier is 32.0 meters per second. We know we're looking for the the projectile at 2.00 seconds. And then we know our acceleration due to gravity is going to be negative. That is 1/2 9.80 meters per second squared. Per second squared times 2.00 seconds squared. All right, there it is. Giving a little bit of weird issues, but it's okay. So meters per second squared. So if we plug all that into our calculator, one second, quick mistake. I forgot to put the sine theta here. So we got to remove all that. This should be multiplied times sine theta, which is 50 because we're only looking for the y direction. So going back, so that's times 2.00 seconds minus 1/2 9.80 meters per second squared times 2.00 seconds squared. So that ends up canceling. These seconds cancel with these meters. So if we plug that into our calculator, we should get y is equal to 29.4 meters using sig figs, because our lowest significant figure is 32.0 or 2.00 seconds, so it's 3 sig figs. So we know that y is equal to 29.4 meters. All right, so moving back to our second question. So at what time t is the projectile at its highest point, and what is the value of the highest point? So like we discussed earlier, and please, if you guys get lost anywhere or if I'm going too fast or anything, please let me know in the chat again. Just make sure we're all on the same page. So we go back to our problem. We know, so we discussed that we know an object at its highest point when its velocity in the y direction is 0. So if we go to our formula, v is equal to v naught plus at. We're looking for when v is 0. So it's v naught y. So we determined that v naught y earlier was 32.0 meters per second times sine of the theta, which is 50 degrees. And so we're going to subtract that by 9.80 meters per second squared, because that's acceleration due to gravity, times t, our unknown. What we can do here, using some algebra, we can determine that t is equal to 32.0 meters per second times sine 50 divided by 9.80 meters per second squared. Meters cancel. This second and this second cancel. Second goes up to the top. We can determine that t is equal to, if we plug that into our calculator, 2.50 seconds using our significant figure. Okay, so using that seconds, we can plug that back into our original formula that we used earlier to find the height. So now we know when it reached the top. We reached the top at 2.5 seconds. If we go back and do it, we can plug that in to y naught plus v naught y times t plus 1/2 at squared. Y is equal to 0 plus 32.0 meters per second times sine 50 times sine 50 times 2.00 seconds minus 1/2 9.80 meters per second squared. And we're just gonna multiply that by, oh, I'm sorry, this should be 2.5 seconds. 2.50 seconds. Multiply this by 2.50 seconds squared. So what do we get when we plug that in? We get y is equal to 30.6 meters. So these are our three answers for questions 1 and 2. This is question 1, and these two are question 2. We'll call this one 2B. Okay, and then so our final question is at what time and what point does the ball hit the ground? So we're going to be done with those two, so we can clear that. And what is the point, and how far in the x direction does it hit the ground? So if we use y is equal to y naught plus v naught y times t, like we did earlier, plus 1/2 at squared, we can determine using some algebra when our ball hit the ground. So we have 32.0 meters per second times sine 50 times t minus 1/2 9.80 meters per second squared times t squared. Using some algebra, we can determine that t, so if we factor out a t, we have 4.90 meters per second squared minus 24. So 32 times sine 50 is 24.5 meters per second. We factored out a t. This is equal to 0, so t is equal to 0, which either, that makes sense. So when the ball never left the ground, it was at the bottom. Or when t was equal to 24.5 meters per second over 4.90 meters per second squared. We determined that t is equal to 5.00 seconds when it hits the ground again. Plug that into our original formula of x is equal to x naught plus v naught x times t plus 1/2 at, just like 1/2 at squared. We know that there's no acceleration in the x direction. We can cancel that. We know that there's no initial x. We can cancel that. That was 0. So we're just left with v naught xt. So x is equal to 32.0 meters per second times cosine of the angle 50 times that time that we just solved for. We can solve for x is equal to 103 meters. So these are our 2 answers for this one. And so, yeah, that's it for today. And it makes sense, right? So, because we know that when t was equal to 0, that makes sense. So it also makes sense that when we solve for 5, that also works. So yeah, that's our first Tuesday VSI session. So every other week, I will have mine on Tuesday, and all those weeks in between, Freya's going to have hers on Friday. Feel free to ask me any questions about this. Send me an email. Come up to me in class later today, or even beforehand. I should have a YouTube link ready for you guys soon. But I hope the session went well. Please feel free to ask me any questions, and that's it for today. All right, no problem. Thank you guys for coming. I hope you have a good day, and I will see you guys in class. All right, thank you.